uh, first SCR followed by, remember the SCR. We have P and P is getting the gate pulse. Here P is connected to anode and N is connected to cathode. We make A equals to positive, K equals to negative, so the SCR is followed by, but unlike a normal diode, it doesn't immediately conduct heavily by because of the three junctions J1, J2, J3. Under forward bias, J1 is forward bias, J2 is reverse bias, J3 is forward bias. So J1 is F, J2 is R, and J3 is F. The reverse bias middle junction J2 prevents significant currents, therefore the SCR is in forward blocking mode. Reverse bias middle junction J2 prevents the significant currents, therefore the SCR is in forward blocking mode. What happens if we keep increasing the anode voltage? Suppose we keep increasing VAK, anode voltage increases, small leakage current, SCR still off. Eventually, if we reach a sufficient high voltage called the forward breakover voltage, the SCR can suddenly switch on even without a gate pulse. This is called breakover. However, we normally don't want to wait for VBO. VBO means breakover voltage. We use the gate to turn the SCR on at a lower anode voltage. That's the normal usage and how the process goes. This we don't apply heavy voltage at anode to get VBO to occur. Gate triggering. Here, suppose A is equals to positive, K equals to negative. The SR is forward bias. We apply a positive gate current IG. The gate is connected to inner P layer. Uh, Here, PNP and PN starts conducting gate files. Then the regenerative feedback we discussed happens, and PN increases, PNP increases, NPN increases, PNP increases, and the SR rapidly switches on. The gate current makes the triggering easier. This is the most important for VA characteristics. Suppose we apply small gate current IG equals to 0. The SCR needs a relatively high voltage before breakover. But if we increase gate current, IG increases, the SCR can turn on at a lower VAK. Conceptually, I the voltage at anode to cathode and here voltage at anode, here current at cathode. So as IG is increasing, the SCR can turn on at a lower VAK. At lower voltage, conceptually turns off. So IG increases as V triggers. That one of the most important SCR characteristics. When SCR turns on, that once the SCR switches on, its resistance becomes very low. Therefore, IA can become large while VAK becomes relatively small. Their current is greater than current at anode is greater. VAK is lower, but still the current is greater. That's the characteristic enters forward conduction region. The SCR now essentially acting like a closed switch. Here the important part, remove the gate. Suppose we trigger the SCR gate pulse SCR on. Now remove the gate pulse. The SCR turns off. No, the regenerative action continues. The SCR stays on as long as a node current remains sufficiently high. That brings us the latching current and holding current. This is the latching current. The latching current IR immediately after triggering, the anode current must rise above a minimum value called IL equal to latching current. The current doesn't reach IL, the SCR may turn off when the gate pulse is removed. So, gate pulse SCR starts conducting, IA rises, IA is greater than IL, gate can be removed, SCR stays on. Here, what's happening? We talked about three things. First of all, this it high voltage at anode, the VBO occurs and the SCR gets switched on, but we don't want the voltage get higher and the SCR gets switched on. Here there is no gate pulse here using. Instead of we do that at low voltage at the gate first, the SCR gets turned on, SCR switches on. Here gate current makes triggering easier. So here gate current at low voltage trigger turns on trigger very easily than we wait for VVO to occur, breakover voltage. Once SCR turns on, current increases max as the EAQ voltage increases to lower voltage, relatively small. Here the important part when we remove the gate, it doesn't off. It still holds the current switch on state. So latching current IL is latching current. If the current doesn't reach IL, the SCR may turn off when the gate pulse is removed. If the latching doesn't reach IL. So latching current IL. Immediately after triggering, the anode current must rise above minimum value called IL equals to latching current. So when the I value, current value, had to reach the value called latching current. It has a value, it will have a definition of it. They will simply get that value by observing the current state. If the current doesn't reach IL, the SCR may turn off when the gate pulse is removed. If we remove the gate pulse when the SCR reaches the IL and it shouldn't be lower than IL, it should be reaches the IL state, IL value. When the gate pulse is removed, if the SCR still holds switch on state, IA. Here that's what he's saying. Gate pulse SCR starts connecting. IA rise, when the IA is greater than IL only, gate can be removed and can the current still be on a switch on state, holding current IH. On the SCR is already on. There is another minimum current needed to keep it on. The SCR is already on. There is another minimum current needed to keep it on. IH equals to holding current. If IA is less than IH, the SCR turns off. So after it is turned on, instead of IL, we call here it is latching current. Here it is holding current. They also may calculate by observation holding current. So as the IA is less than IH, the SCR turns off. Usually IL is greater than IH. Why? Because turning the SCR on and keeping it on are not exactly the same requirement. Are not exactly the same requirement. Because turning the SCR on and keeping it on are not the exactly same. IL is latching current. Latching current is if IA is less than latching current, it will not be in switch off state. So IA is greater than latching current only. The switch on state happens. Here holding current is IH. So IA must be greater than the holding current to be switch on state. That's do you remember this? You will remember this and this. Yeah. So IA should be greater than IH. If IA is less than IH, then it is turns off. Here two things can happen. I think if IA is less than IH, and it cannot be greater than IL if it is less than IH, because IL is greater than IH. Complete SR characteristics. Now you can understand the whole graph, current and breakover voltage. Here the on, reverse blocking. Are there are the three major operating modes? Reverse blocking VAK is less than zero. Forward blocking VAK is greater than zero. IG equals zero. SR forward bias remains off. Forward conduction gate pulse off. Breakover causes SCR. Here we can forward conduction happens in two ways. We can give voltage at gate or we may give uh, anode to cathode a big voltage so that VO occurs, VDO voltage breakover. The SCR gets turned on. The substantial anode current flows. The four values to remember: VDO block power voltage, breakover voltage, IG base current used for triggering, IL latching current, IH holding current, and the key relationship IL is greater than IH, and IG increases, V triggers. That means um, V gets at lower voltage, current is maxed at V. Next, we should learn the SCR is actually turned on. We should learn how an SCR is actually turned on, especially the difference between actual communication. As you have already covered CB, CC, and you can add those also. RC coupled amplifier. The syllabus specifically says RC coupled and crystal. Let's understand what RC coupled actually means. This is my syllabus. Crystal and demon. RC coupled and crystal amplifiers. Let's understand what RC coupled actually means first. What does coupling mean? Suppose we have two amplifiers stages, amplifier 1 and amplifier 2, and the output input gives to amplifier 1 and amplifier 1 to amplifier 2 and amplifier 2 to the output. The first amplifier's output needs to become the second amplifier's input. The method used to transfer the signal from one stage to the next is coupling. So, to an amplifier, uh, coupling means this is an amplifier, this is an amplifier. It doesn't state what kind of amplifier. Two amplifiers are there, input and output. The first amplifier outputs becomes to the second amplifier's input. The method used to transfer the signal from one stage to the next is called coupling. In the RC coupling amplifier, we use the resistor plus capacitor. The capacitor is the coupling component. So this is one amplifier. What does an amplifier do? It amplifies the signal from a low frequency to high frequency. It converts the low frequency signal to high frequency by using a source or without a source. It can accomplish that also. Like usually AC signal, it converts low frequency to high frequency. Then like it reaches like for a microphone example, the AC reaches and the voltage battery source. We use BJT transistor to amplify it to high frequency. That's way the amplifies the signal. So here amplified signal again goes into another amplifier to again get the max of output out of it. So this process is called coupling. The second amplifier's input is the first amplifier's output. The RC coupled amplifier we use the resistor plus capacitor as a coupling component for couple this like input and output. I think in between resistor and capacitor. Why do we need the capacitor? Imagine two C common emitter amplifier stages. Like imagine two common emitter amplifiers, stage 1 and stage 2. We use the capacitor as coupling. Here it is. Let's see. The coupling capacitor is AC transfers the AC signal from Q1 to Q2 but blocks the DC voltage. So here it converts here coupling capacitor DC transfers the AC signal from Q1 to Q2. So I don't understand. Q1. Uh, Common emitter, he said. For a common emitter is gives nothing. Base gets input and col- collectors get output. So I think this is base and this is collector, and here coupling is happening. Blocks to result. That is extremely important. Why the block DC? Each transistor needs its own proper DC biasing. For example, Q1 needs its own bias point, Q2 needs its own bias point. If we directly connect them, the DC voltage or current from Q1 could disturb Q2 bias. So the capacitor essentially says AC signal can pass, but DC bias should stay separated. How does the signal travel? Suppose a microphone produces a tiny AC signal, microphone Q1 amplifier signal AC. So these are inputs. I think. Q1 and Q2 are first input of the first input, then amplifies the AC. The microphone to Q1. This is the amplifier. Sorry, this is an signal. AC signal is Q1. Here amplifier amplifies the AC signal to get gain. My amplifier gain. Then the capacitor sends only the AC, blocks the DC. So Q2 gets the first input output of the first amplifier as the input of the second amplifier. Then it amplifies again. It gets to the speaker. The coupling capacitor passes the change in signal. AC passes, but blocks steady state DC. So multiple amplifier stages can be connected without disturbing the individual bias conditions. Why RC amplifier? The amplifier stage itself generator generally has a collector resistor RC, while the stages are capacitively coupled. A simplified two-stage RC amplifier. Input is go to base, DC is connected here. It is RC and resistor at the collector. Here a resistor to emitter and this is Q1. Here collector to emitter. B getting the input. C E is connected. Emitter is connected to the output here. It is RC. It is common collector. This is so. This is common collector. This is also common collector. Uh, this is nothing else. This common collector and capacitor couples and the voltage goes to RC2. The input goes to as VCC of RC2 and the resistor collector at resistor at the collector and it goes to emitter and then ground output. The CC between stages is the coupling capacitor. What happens to frequency? This is the exam important. The coupling factor has resistance Xc equals to 1 by 2 pi Xc. The coupling capacitor has a resistance Xc equals to 1 by 2 pi Xc. I think this is the capacitor formula, right? 1 by omega at low frequency. At low frequency, Fc decreases, Xc increases, so the capacitor doesn't pass the signal as effectively. At mid frequencies, Xc is relatively small. The signal passes well. So resistance of the capacitor is low as As frequency decreases, X increases. Uh, so as the capacitor doesn't pass the signal as effectively. At low frequencies, it doesn't cross the signal effectively. At mid frequencies, X is relatively small, so signal passes well. At mid frequencies, signal passes well. At higher frequencies or other transistor internal capacitances begin affecting the gain. Therefore, an RC coupled amplifier generally has a mid frequency region where gain is relatively constant. So here gain, look at the frequency gain. Uh, Gain and the frequency. As the frequency is low, there's no gain. As it reaches the mid, it gets the high gain. When it is high, the other transistors and internal capacitors begin affecting the gain. Generally has a mid frequency region where gain is relatively constant. So it gets to a constant state. At higher frequencies, for oscillators generally have a mid frequency region and lower. But why is RC coupled popular? This is for frequency response. Why is RC coupled popular? Because it provides a good voltage amplification, relatively simple circuit, good frequency response in the audio range, low cost, portable for multi-stage voltage amplification. So good voltage amplification because we are using two amplifiers. Like basically we can say they are series. Amplifiers are in series. Relatively simple circuit, good frequency response in the audio range, low cost, suitable for multi-stage voltage application. Ideally not, but it is not ideal for transferring large power to a speaker. But that's exactly where it not gets started. Push up amplifier becomes useful to halves of the signal. It is mainly used as power amplifier, unlike an RC coupled amplifier, which is mainly used for voltage amplification. Why do we need it? Suppose we want to drive a speaker. We want to send the input the speaker. Suppose we want to drive a speaker. A small microphone or signal might be. This is a small microphone signal might be. This a transistor amplifier can amplify it, but a single transistor arrangement may not effectively handle both halves of large AC signal. The amplified signal is large after amplification. It may be AC amplified, but it cannot drive to the towards the speaker. We need a help of transistors to do that. So we use two transistors. Basic idea for a complementary push-pull amplifier, input goes VCC, output to the speaker. Actually, Q1 is NPN and Q2 is PNP. They work on opposite halves of the cycles. Like positive half cycle, suppose the input becomes positive. The NPN Q1 conducts more strongly. Positive input NPN Q1 gets on, current delivered from load, output positive. So Q1 effectively pushes current into the mode. Negative half cycle, now the input becomes negative. The PNP transistor Q2 conducts negative input, PNP Q2 on, current flows in the opposite direction. Output is negative, Q2 effectively pulls current from the load. That's where the name comes from, push and pull. One transistor pushes, the other pulls. Why is this useful? The two transistors together reproduce the complete AC waveform. Q1 is positive half, Q2 is negative half. So we can deliver significant AC power to the speaker. Class B operation. A basic push-pull amplifier often operates in Class B. Each transistor's conductor conducts for approximately 180 degrees of the input cycle. So Q1 is plus of 180 degrees, Q2 minus of 180 degrees, together 360 degrees. Then the entire signal cycle is reproduced. The problem, cost over distortion. Here the important disadvantage. For a silicon BJT unit roughly needing similar to 0.7 volts before it converts significantly according around zero crossing input positive negative. When the input is very close to zero, neither transistor may be sufficiently on. So the output can have a small edge. This is called crossover distortion. Class AB solves this. Instead of keeping both transistors completely off around zero, we give a small forward bias. Then each transistor conducts slightly more than 180. So 180 is less than theta is less than this. This is called class AB. Class P, Q1 180 degrees to 180 degrees crossover distortion. Class AB, Q1 is slightly greater than 180, Q2 is slightly greater than 180. Much less crossover distortion. This is a very important exam comparison. So RC coupled versus full scale. The RC is used to voltage amplification. It is a power amplification. Usual output stream here multi-stream. Usually RC uses RC coupling minus complementary opposite transistors. Good for small signals, good for driving those. Common in audio voltages, common in audio power stages, not designed for high output power, designed for high output power. Remember this same microphone small signal offset of large signal. Large signal is useful power amplifier for sending large signal. Here, that's to go little deep thinking. So the output greater amplified signal is getting to input. So this is PNP, NPN. This is PNP. So this is pushing here. NPN is pushing. So NPN on current delivered to load, output positive. So Q1 they effectively pushes current into the load. So here NPN is pushing towards the output. Okay. Here Q2 is pulling Q2 output negative. Q2 effectively pulls current from the load. That's where the names come push and pull. Here it is pulling towards the load. This is pushing here. It is pulling here. Push and pull. And the output goes to the speaker. So what's the problem here? So what was the problem here? So the problem is so IM is useful that two transistors reproduce the complete AC waveform. The two transistors reproduce the complete AC waveform. So you can deliver significant AC power to the speaker. So power doesn't lose. You can deliver significant power. The problem is the intracycling reproduce 360 degrees. The problem goes of distortion. For a silicon BJT we need when we use BJT we need B 0.7 before it conducting significantly around zero crossing. When the input is very close to zero, neither transistor may be sufficiently on, so the output can have a small edge. When the input getting the AC signal, amplified AC signal, for example from RC couple, the NP and PNP are not getting the enough B 0.7 volts. So it didn't have the so it didn't get switched on. So at the beginning there will be a dead zone. We don't have, we lose some information. So this is called crossover distortion. Also class AB solves this. So class AB instead of keeping both so at the beginning only we give some small forward bias voltage to the transistor. Then each transistor conducts slightly more than it. They are getting voltage slightly greater than 90 theta. Crossover distortion use class AB. Q1 is 180 degree, greater than 180 degree. Q2 is greater than 180, much less crossover distortion. This is very important in some com comparison. So that's it. If you think how NPN pushes and PNP pulls, NPN is NPN. Uh, let's use simple complementary interrupt follower. So this is NPN input getting to the base emitter, emitter, PNP base. The two emitters are connected together at the output. The two emitters are connected at the output. Suppose the input goes positive, the NPN becomes NPN base becomes positive for NPN. V equals to 0.7. So the NPN times on. Here the NPN times on, then base becomes positive. Current can flow from NPN towards speaker. The NPN is supplying current from positive supply into the load. That's called pushing current in the load. Negative half cycle PNP push. Now the input goes negative. The PNP turns on. So why this is like this? Like for NPN, we give positive P and P ripples, and the holes in the P ripples. Here for P and P, we give negative. So electrons in the N ripple. Now the current path is reverse. So the current flows from P to holes. As we know how the NPN and PNP work, if we look at my LinkedIn now, I pasted the now the current path is reverse, so it is going to the speaker to PNP voltage. The PNP provides a path from the output toward the negative supply, so effectively pulls the current out of the load or output. So it effectively pulls current of the out of the load or output node once negative half cycle pulls. PNP is pulling. Hence, so important don't think NPN always pushes and PNP always pulls. The times I described the role in the complementary crystal output stage. The real reason is their transistor behavior. NPN IC increases when base becomes positive, supply current positive toward the load. PNP IC increases when the base becomes more negative. So end becomes more negative, provides the return path toward negative voltage. So NPN supplies current if PNP sinks current full. So, NPN current load from as negative and PNP current mostly good in my chemistry repeated. As you were thinking of a conventional current in the state system, I think that's the right general answer. And NPN as conventional current goes from to the transistor is called approximately C to U. So in the push-pull stage, current comes from positive supply. So positive to negative output gets negative side, output is negative side. So we call NPN push transistor because it supply current over the positive. This is the most understandable way to understand. The PNP conversion current is enter to collector. So but the because PNP is connected to the negative supply in the complementary push-pull stage, the load currently is the opposite direction. The PNP convenience current is entered to collector, but because it is getting a negative voltage in the complementary principal stage, the load current is in the opposite direction. So the load current is in opposite direction. So it pulls current from the output toward the node, toward the negative supply. I mean, but don't say ambient current always goes positive to negative and PNP always goes negative to positive. That's good. God, the better rule to memorize ambient current, yes, collected to enter. PNP is entered to the push behind difference from those strands are connected in the circuit. So it is also entered to collector. This is collector to enter. So the diagram, this is collector to enter. It is going, but here it is enter to collector. It is the output. But due to it is getting a positive negative voltage, it was flipped towards the output negative. So the current goes in the negative towards negative output. So that's why it pushes the basic signal and this is pulls the signal, outputs that to the speaker. That's the amplifier. An amplifier doesn't have the same gain at every frequency. So the amplifier composition techniques in amplifier. The main idea is compensation is needed to improve or stabilize the frequency response of an amplifier. An amplifier doesn't have the same gain at every frequency. For example, there are three regions: low frequency, mid frequency, high frequency. Low frequency gain decreases, high mid frequency gain approximately constant, high frequency gain decreases. We think we studied this in RC coupled. Why does gain fall at low frequency? Mainly because of the coupling and bypass capacitor. So coupling capacitor, remember in our RC coupling capacitor. The capacitor's reactance is actually equal to RC, which is the reason. Why does the gain fall at high frequency? This is the more interesting. A transistor contains internal parasitic capacity. The transistor has an internal capacitance. For example, the transistor junctions have capacitance at high frequency. When F becomes very high, this becomes very high, Fc decreases. So these parasitic capacities begin providing significant path for the signal. The result is gain falls at high frequency. Gain falls at high frequency. Is the result. So what is compensation? We deliberately add components or networks to counteract the undesirable frequency effects. The goal is usually to extend bandwidth, stabilize gain, prevent unwanted oscillation, improve frequency response. This is called frequency compensation. So gain is falling at high frequency. So what is he saying? So what is combined? We deliberately add components or network to counteract undesirable frequency effects. So we don't want any undesirable frequency effects, like any effects happening, high frequency, gain is falling. So the goal is extend bandwidth, stabilize gain, prevent unwanted oscillations. Extend bandwidth, stabilize gain, prevent unwanted oscillations, improve frequency response. This is called frequency compensation. Common compensation techniques, capacitive compensation. The capacitor is deliberately added to modify the frequency response. Miller compensation. A capacitor is connected between the input and output of an amplifier stage. Uh, because of the amplifier's gain, the capacitor can appear much larger from the input side. This is called Miller effect. It helps control high frequency behavior and can improve stability. Lead compensation. A network is designed to introduce a phase lead over the selected frequency range. Lag compensation. A network introduces a phase lag. For your current electrolytic you mainly need concept of compensation. In later, you linear control response towards separately mentions lead lag compensation techniques, which is different context. The example of decay, remember the tune amplified gain varies with frequency, no frequency, coupling bypass capacitor effects. So capacitor effects, mid frequency, approximately constant gain, high gain, transistor parasitic capacity. Compensation networks are used to obtain a desirable stable frequency response. So one input don't mix up amplifier frequency compensation. Controlled amplifier frequency response stability. Need the compensation control systems. Modifying the control system for the syllables contain both but will treat them separately. Next is feedback. Continue. Next is feedback, and this is very important because it leads directly into negative feedback and the oscillator. Feedback in amplifier. What is feedback? Feedback means taking some portion of the output signal and feeding it back to the input. Basic idea, input, amplifier output. Uh, Input is amplifier output. It gets feedback from the output and we go back to the input. So the amplifier output is sampled and count some of it return to the input. Why would we feed output back to the input? Because feedback can change the amplifier behavior. It can improve these things such as gain stability, bandwidth, distortion, noise, input-output impedance. But the effect depends on the whether the feedback is positive or negative. Two types: positive feedback. The feedback signal supports or adds into the input signal. So input plus feedback, positive feedback is very important in oscillators. Negative feedback. The feedback signal opposes or subtracts from the input signal. So here output takes some part and add to the input. Here output feedback takes some part and subtract to the input. And again give to the subtract to the output of the input. That's what happens in negative feedback. The feedback factor beta. Suppose the amplifier output is V0 and only a fraction of it is returned. We call that fraction the feedback factor. Therefore, Vf equals to beta V0, where Vf equals to feedback voltage, V0 equals to output voltage, beta equals to feedback factor. So the feedback factor beta. I think we seen this in somewhere. We seen this somewhere. Negative feedback. Suppose the original output